go to the last step, which is determining the nomological validity of the constructs, right? So now I go to my model again and I save this model. Okay, I save this model as this is my measurement model. Now I save this model and call it as structural model. So I give it a new name and I call it as structural model. What is going to be in structural model? The structural model will now have nomological parts. It will now have relationships. So now I delete these three covariances. Okay. What do I do now? Because I want to remember this diagram that I had shown on the whiteboard, we now want to test these paths. Okay, we have shown that these constructs are discriminant from each other, and I now want to test these paths. So what am I going to do? I am going to draw paths, not covariances now. I'm going to draw paths from my construct to the other construct and path from Pj as well to Cb and okay. Now because these are structural paths, remember I told you that when you have, now this is x, leadership is x, Pj is y, so this will have its own error. This will have its own structural error. So we will call this, we will attach an error to Pj. Similarly, we have an error associated with CPP because now this is going to be determined by our model. These are now both PJ and CPP have become endogenous variables to our model, variables that are going to be determined. In this model, there is only one exogenous variable, that is independent variable, that is not determined in our model, and that is mean. PJ, CPP, and all the observed items, they are all endogenous variables that are actually getting determined by our. So let us name these two errors also. I will call them as structural error 1, structural error 2, right? And yes, all these relationships are theoretically determined, right? You will have to cite the literature in order to make case for, remember that OCB paper as well as the family role performance paper that we have seen earlier, right? PJ is a mediator here. PJ is not a moderator, PJ is a mediator. What is a mediator? Mediator is caused by the independent variable and it causes an outcome variable. So it mediates the relationship between leadership to outcome. So this, anything that goes in between is called as a mediator variable, right? So PJ acts as a mediator. PJ is discriminant from leadership. CPP is an outcome variable which is also discriminant from leadership, and you can have as many mediators as you like. You can have multiple mediators. Okay. Now this is our model. Now when we go to the output, okay, we have this, and we also now want to show, because now we are checking paths, we are testing effects, so we ask the tool to give indirect, direct and total effects also. So we want the tool to give us. And now for the first time I want to do, because I know I have been testing this model again and again and I have seen that these are non-normal data. So I'm going to do bootstrapping. I want the tool to report bootstrap results also for all the effects that we have been computing. Now, what is bootstrapping? Bootstrapping is a method which tackles non-normality. So if you have non-normality in the data, which we have already seen, okay, we have already seen it is non-normal. So bootstrapping is a method by which we take or tackle non-normality. There is a literature behind it. I don't want to digress at this time, but just for your understanding, remember that if there is non-normality in your data, it is always useful to report the bootstrap result. And when you will have bootstrap result, okay, you will report two things. You will always report in bootstrapping, you will always report when you talk about bootstrap, sorry, okay, you will report the beta, the bootstrap coefficient. So you will get all the coefficients just like you get in normal SEM analysis. So you will get the coefficients, let me call this as coefficient. You will also get a p-value, you will get a standard error, we'll see it in a while, and you will also get the lower limit of confidence interval and a upper limit for confidence interval. So usually we check for 95% confidence interval, right? So we test for because of our 5% significance levels. So we will get a lower limit and this is called as lower limit of confidence interval up. Sorry, it is not UP, it is ULC. Okay, upper limit of confidence interval. What you've got to check that in this interval, 0 should not lie. Okay, 0 should not occur in this interval. Let's say you get an interval of 0.05 to 0.15. Now 0 is not between 0.05 to 15, and therefore what will you conclude? That your beta is significant. Beta is significant at 5% level of significance. Okay, so you should zero is a number, right? Remember what is the test that we are checking? Our test is beta is equal to, hypothesis test is beta is equal to 0, beta is not equal to 0. Beta is what? Beta is regression coefficient. And what is the test in regressions? We want to have our regression coefficients not equal to 0. And for that, when you do bootstrapping, remember bootstrapping will be done for non-normal data. And if you look at this book of Amos and doing things, this SEM using Amos, the chapter number, the book has a chapter which is dedicated to chapter number 12, if you see, bootstrapping as an aid to non-normal data, 329. Okay, so when you do that, okay, please, if you have non-normal data, and we saw in our previous runs that the data that we were getting is non-normal, so you should always do bootstrapping, and that is what I am going to show you right now. Okay, so you should, when you are testing this hypothesis, beta is equal to 0, beta not equal to 0, look for the bootstrap coefficient, you will report this as well as the confidence interval. So you should always report. Okay, so let me go and do this. Now when you are going to test this, remember we can, so usually you tell the tool to generate some bootstrap samples. Okay. Now, usual number that we should set here is about 5,000. Remember, the more samples you ask the tool to run, the more effort it is going to take. So 5,000 is a good number, okay, where you can, some people suggest you can go up to 10,000. Don't go beyond 10,000 at all, okay. That is a waste of computing resources. And then report bias corrected confidence interval, and I am going to set it at 95%. Okay, so these are the two picks that you have to perform. One is bootstrap samples, select 5,000 samples, or maybe go up to 10,000. Don't go below 5,000, have at least 5,000 samples. And then bias corrected confidence interval. We want, if you want 90% confidence interval, put it 90. If you want 95%, if you want 99%, then put 99. But usually, if you can show good results for 95% confidence interval, I think you are right. You are doing that. Okay, you can do this earlier also. You can do it in measurement model. You can do it in when you are doing separate runs also, but you will get similar runs, similar output, because here also measurement model is automatically getting tested. Remember in SEM, we said that the beauty of this method of structural equation model is now we are going to ask the tool to run this complete model. So we are going to, let me take a try of annotating here. Okay, if you, so this is what we said, this is our measurement model for leadership. Okay, this is our, our measurement model for PJ, and this is our measurement model for CPP. Right? So I have done, I'm going to do, even when I run this together, I'm going to do all the three measurement models here. So you are going to get anyways you are going to get this run here, the same kind of one. And also the second thing that the tool is going to do is we are now going to run this is what we call as the structural model. Structural model, remember, it is always related to latent paths between latent factors, right? So this is what we call as econometrics. Remember yesterday I was telling you that SEM is a mix of econometrics as well as psychometrics. Right? These measurement models are what we call as testing for the measures, right? Testing for our scale. So we are now going to do both of this right at the same time. This is going to, right? And let me just So now we have this. And this. Okay. So we have in our analysis properties, we have already selected all of this. And now I'm going to, okay. And this is our output. Let us see the output. Now you see the first of all the fit of the model of the structural model. It is going to be exactly the same as the fit of your measurement model. So if your measurement model is good, your structural model will also be good. Our chi-square is 206 degree of freedom. Our relative chi-square is 1.623. Okay, GFI is 0.96, CFI and RMSE. This is exactly the same index that we had during our measurement model. So what are we saying? That our measurement model fits well with the data. This is a good model, and therefore the results that we are seeing here can be sort of accepted and reported in the research paper. Now go to the estimates, okay, and we are seeing path from lead to PJ. This is a path. This is the unstandardized regression weight 0.68. So the beta is unstandardized and it is significant. Then leadership to CPB, it is 0.219 or 0.22, and this is also significant at P less than 0.001. Remember, 3 star means less than 0.001. And then PJ to CB, this part, PJ to CB is also 0.09 and it is significant at P less than 0.05. It is P less than 0.05. And if I have to draw this, if I have to write this by hand, if I will have to do this, what will I do? I will say the unstandardized or the beta coefficient. How will I report it? I will say my beta coefficient is, how will I report this in my research paper? I will say I have lead, I have PJ, and I have CPB. Okay, this is the path. Beta here, unstandardized regression coefficient, leadership, this is 0.54. Okay, and what is its significance? Significance is 3 star. Okay, I will actually let it remain at 2 star. I will call this as P less than 0.0. It is actually less than 0.001, but I am just saying it less than 0.0. Then CPB, PJ to CPB, it is significant at 0.05, and what is the standardized coefficient? It is 0.15. I will call this as beta is equal to 0.15 and 1 star. What is 1 star? 1 star is less than 0.05, and lead to CPB, it is 0.28, and what is the significance? It is 3 star. So this is 2 star. Okay. This is what I have. This is the output of my result. Now when you click on estimates, you will see you can click on exactly total effects. Okay, this is the total effect. Okay, so estimates, if you open it up, you will get to scalars. Scalars are regression weights. This is the unstandardized output. These were what we were seeing. and the standardized regression. This is what we have reported, leadership to PJ. Now, the moment you click on this standardized regression rate, you will see there is in this window, you are also seeing Bootstrap, estimates Bootstrap. Now, when you click on estimate Bootstrap, so Bootstrap estimates are the same that you are getting here, Bootstrap estimates, and you get standard error. So estimates are the same, but what is important is you will get bias corrected confidence interval. So this is estimate, okay? So we have got Bootstrap estimate leadership to PJ, it is 0.54. And what is the Bootstrap confidence interval? So you will make a table, in your papers similar to this, and you can say, okay, I will make a table here, and when I'm going to report, I will say this is my path, this is my data, and so I will call this as the first row, I will call it as path. I will call the estimate, and I will call this as lower limit of confidence interval, upper limit of confidence interval, and you can report that the confidence interval has been computed, or you can just say bias corrected %95 confidence interval computed based on 5,000 bootstrap samples. What is the path? The first path is lead to AJ. What is the estimate? It is 0.54. Okay, and the lower limit is 0.43, and the upper limit is 0.62, and the p-value is it is less than 0.000. So you can, it is significant. You can also have a column here, and then the next path that you have is AJ to CPB. What is the coefficient? PJ to CPB, it is 0.15. The lower limit is 0.02, and upper limit is 0.27. P value is 0.03. So we will call this. And then CPB, sorry. We will have lead to CPB, it was 0.28. The lower limit is 0.15. Upper limit for lead to CPB is 0.1. P value for this is again less than. Now the same thing you can do even when you are measuring for the items of your latent constructs. So you see you have EMP, EMP to EMP3 when you are reporting CFA results. The same thing, the same kind of table you can draw. You can say that this is my coefficient, this was my loading, EMP3 on EMP, it was 0.81. The standardized loading is 0.81, lower limit is 0.77, upper limit is 0.82, and it is significant at 0.01. Because this is 0.001, so you cannot write it is less than 0.001. So for this, you will write it is less than 0.01. Similarly for second item, third item, fourth item, and so on, right? So basically, even when you had data non-normality, right? When we saw that the data was non-normal, this is the uh, this is the table that you will report and say that you see this was my coefficient and I ran bootstrap samples. I ran 5,000 bootstrap samples. I computed the bias corrected 95% confidence interval, and my confidence intervals, 0 is not lying in these confidence intervals, and therefore I can say that my, even correcting for non-normality, I have significant results that can be accepted and believed, right? So that is what we are doing here. We have shown that. So where did we start? We started by saying that we developed these scales, right? We developed this, we did EFA, then we did CFA, then we brought in two different constructs. We showed that this construct is discriminant from these constructs, and then we showed that the relationships also hold good. That means now I have proved what all have I proved here now? I have proved, first I talked about content validity. Content validity was what? It was qualitative. Remember, we said we will define the construct, we will write, develop items, so we will generate items, item generation happened, right? And we will do phase validity. This all goes in the domain of content validity. This how does this take place? This takes place using, based on literature reviews, lit reviews, interviews, practitioners, interviews with practitioners, practitioner inputs, experts, and so on, right? Self. Then what did we do? We came to the second one, right? We came to the second part of validity, which was convergent, or we call this as, yeah, construct related, convergent, and discriminant. Where we showed using AR, ABE, we showed that the constructs has items that load properly, right? Here what did we do? We also did, we did EFA, we did reliability, and then we did CFA, where we, through CFA, we computed CR and AB. And then here we also showed one construct has items that load properly, and then we showed construct is discriminant from other constraints. And then lastly, what did we do? We did logical validity, right? Where we tested relationships between discriminant constructs as determined or suggested by theory or literature, and we showed that our construct captured through measure developed by us or by us is related to other constructs as expected. As expected. Right? So we have done all of this in order to show that the scale that we are developing, this scale is the right measure for the construct that we and for non-normality you have bootstrap results, and using this you can report all of. Okay, let me